Welcome, everyone, to this explainer. If you're the kind of person who just absolutely loves ripping things apart to understand exactly how they work from the ground up, well, you're definitely in the right place. Today, we're tackling a really fascinating foundational question. How do we actually translate the raw, chaotic flow of physical reality into a structured computational language? We're going to be looking at the exact methodology that engineers and researchers use to assign computational directionality within physical systems. It's honestly an incredible journey, taking the wild, unpredictable behavior of physics and giving it clear, flawless logic.
Okay, let's dive into this with a statement that completely flips how we usually think about mathematics and reality. The source material presents this incredible philosophical hook. Nature integrates, only mathematicians differentiate. I absolutely love this quote. It immediately challenges our deepest assumptions about math. It kind of suggests that the highly complex way human beings have been trained to calculate and solve problems on a chalkboard might actually be fundamentally at odds with how the physical universe simply operates all around us.
To unpack that profound idea, here is our roadmap for today's explainer. First up, math versus nature's logic. Next, the integral causality preference. Then, mapping with causal strokes. And finally, we'll bring the whole shebang together with the SCAP flowchart method. All right, moving right into part one, math versus nature's logic. Let's examine that grand philosophical contrast between how we calculate things and how nature actually behaves.
So there's this really stark contrast between human logic and physical reality. As humans, when we model systems, we tend to rely heavily on differentiating. Think about how we're taught in school, right? We look for the slope of a curve. We break things down into these instantaneous little snapshots, and we try to calculate complex, immediate rates of change. And man, it requires some heavy computation. But physical reality, it naturally integrates. It accumulates. Nature doesn't hit pause to calculate a derivative to figure out what happens next. Actually, scratch that. It's more like nature is inherently lazy in the absolute best way possible. It simply gathers and builds up energy over time. It just takes what it's given, accumulates it, and moves forward. This represents a massive fundamental disconnect between how we try to force mathematical calculations and how the physical world actually unfolds.
Which brings us perfectly to part two, the integral causality preference. Let's ground this somewhat abstract disconnect into a highly tangible concept.
In modeling, this idea is defined as integral causality. It's basically the natural preference of physical systems to sequentially accumulate energy over time. To visualize this, just think of a super simple real-world analogy, a bucket sitting under a running faucet. The bucket doesn't care about the mathematical derivative of the water flow. It's not sitting there calculating the acceleration of the drops. It simply fills up. It sequentially accumulates the water. In complex physical systems, whether that's a capacitor accumulating electrical charge in a circuit, a thermal mass soaking up heat, or a mechanical spring continuously storing force, this continuous sequential gathering is the absolute essence of integral causality. Nature, at its core, naturally acts as an accumulator.
So, the crucial point is, our ultimate goal in modeling physical systems isn't just to do abstract math for the sake of making things complicated. Engineers generally hate doing unnecessary math, right? Our objective is to structure mathematical logic so that it genuinely reflects the actual behavior of nature. We want our equations and our computer models to flawlessly mirror the reality of that sequential energy accumulation. If nature prefers integral causality, well, then our computational directionality must be purposely structured to honor that exact preference.
Okay, so we know what nature prefers, but how do we actually visualize it? That brings us to part three, mapping with causal strokes. What's the analytical tool that makes this translation possible?
The solution here is what researchers call a causal stroke. It's a systematic visual procedure used to assign computational directionality within a physical system. Imagine drawing a line connecting two physical components on a diagram, and then adding just a short little perpendicular mark at one end of that connection. That single little stroke is an incredibly powerful tool. It takes this massive, tangled web of abstract physical interactions and gives it strict, readable logic. It clearly maps out exactly how energy is flowing and accumulating from one component to the next, without leaving absolutely anything to guesswork.
And this brilliantly illustrates how that single stroke forces us to make a definitive choice. Which variable is the cause, the input, and which is the effect, the output? Let's use a rapid-fire example. If you push a block across a table, is the force you're applying the cause and the block's resulting velocity the effect? Or is the velocity the cause and the force the effect? In reality, it has to be one or the other, based on the system's boundary conditions. The causal stroke serves as a definitive marker to clearly distinguish between these two states. By formally deciding and mapping out the input causes and the output effects, we perfectly align our mathematical equations with the unyielding flow of reality.
But how do we scale this up for an entire system? That leads us to part 4, the SCAP flowchart method. Let's turn everything we've learned so far into a highly practical, step-by-step procedure.
To apply the causal stroke across a really complex, multi-layered system, researchers rely on an algorithm known as SCAP. SCAP stands for the Sequential Causality Assignment Procedure. Basically, it takes our preference for integral causality and that visual tool of the causal stroke and packages them both together into a foolproof algorithm. It completely eliminates the guesswork and human error when you're assigning logic throughout massive, complex computer models.
Let's move to and see how this builds. If you're analyzing a system using the SCAP flowchart, you follow this precise sequence. Step 1, assign sources. You establish where the energy is fundamentally entering the system. This means finding the external drivers, like a battery supplying voltage or a motor applying torque. Step 2, propagate through junctions. You follow that energy as it branches through the connections. These are these structural pathways, like gears or parallel electrical wires, distributing the cause and effect relationship right through the system's architecture. And finally, step 3, assign preferred interval causality to storage. This is the crucial moment where we truly honor nature's logic. We make sure that components storing energy, like mechanical springs, flywheels, or electrical capacitors, are mathematically treated strictly as accumulators. By following these exact steps, we ensure every single part of the model perfectly reflects the integral causality we discussed earlier.
By mastering the SCAP methodology, our ultimate learning goal is achieved. You are now fully equipped to use the causal stroke to systematically separate the drivers, the causes, from the reactions, the effects. You can take any chaotic real-world physical system and assign flawless computational directionality to it. And most importantly, you're honoring the way nature organically builds up energy, which gives you incredible analytical clarity and vastly reduces the likelihood of computational errors.
Which leaves us with this final, vital question to ponder as we wrap up this explainer. Does your mathematical logic truly reflect the actual behavior of nature? Remember, nature integrates, while only mathematicians differentiate. As you look at the systems, the data, and the models in your own studies or work, I really challenge you to ask yourself if you're just blindly crunching abstract numbers or if you're genuinely mapping the sequential accumulation of reality. Thank you so much for joining me today to explore the beautiful logical physics and keep questioning how we model the world around us.